Okay, so welcome to Database Systems. I'm Daniel Kopta. I go by Danny. You can just call me Danny if you want. So this is the non-grad level, non-advanced databases course, which means it would be more about understanding the use and design of databases in applications and software, and less about how would you go about implementing a database engine. But we will talk about that because you have to understand it at least enough to know what you're doing in using a database. Is this loud enough for you in the back? Okay, let me see if I can. Is this working? Yep. Okay. So, data is right there in the name of the class, what it's all about. Computers obviously are all about data. That's all they do is move and manipulate data. So let's talk about the domains of data that you've seen and then what we will see. So here's the CPU. This is basically the whole point. There are databases out there, there are data centers out there, big disks, memory and everything, but the only purpose of all of that stuff is at the end of the day to somehow get some bits to the CPU. Right? The CPU needs instructions and data in order to make anything happen. So it has registers and caches. That's basically, as far as the CPU is concerned, that is data. That's where data lives. And this domain, this realm of the data is basically the compiler's concern. So going from a register to anywhere beyond a register is the compiler's decision. Right? It has load this address into a register, do something with it in registers, store that register to this address. Okay, and then beyond that is main memory, or DRAM. Usually it's implemented with DRAM. So if the cache, gets full or something else kicks your data out, then it goes to DRAM. The compiler doesn't know or care about that. And this is kind of just the system automatically doing it for you. And then beyond that, you have the disk, so this is kind of the picture that we have so far, and this is like the picture pre-internet days. So this translation level, going from DRAM to disk, that's kind of the operating system's domain or decision when it needs to evict something from DRAM to disk. The OS is what decides how to do that. So all of this, I'm showing all of this as just this big blob of data storage. So you usually think of data, of disk data, as you explicitly open a file, read to it, or write from it. But really the disk is just another cache for DRAM, right? So if DRAM gets full, or if you swap in another process or something, that data can be automatically, by the operating system, evicted to disk. So the way we're looking at this is from the CPU and compiler's perspective. Anytime you do a load or a store instruction, it may go as far all the way as the disk. Question back there.
That was another kind of RAM, right? Was it SRAM?
No, SRAM is, so the disk is SRAM? Is that your question?
I'm asking, is there another kind of RAM?
Oh yes, there is. So DRAM is main memory, usually. SRAM is what the caches are made out of. It's just a different physical way of manufacturing RAM. But anyway, so as far as the program and the CPU is concerned, like all of this stuff is just data storage. It's out there somewhere, and all of these translation levels are applied automatically. So all of this, though, is the programmer's domain. This is what you have seen. This is what the way you could think of computing like pre-internet and pre-data center or big data days. You as a programmer have to be aware of all this stuff and how it works in order to write efficient programs. And it's pretty simple if it's just this picture. But then you get the internet. So you take all of that stuff, put it into a computer, and then that computer is now talking to other computers that are out there somewhere, like Google, Facebook, Canvas. And those computers are specifically designed as, they're basically data storage, vast data storage. So Facebook, they have tons and tons of data. Google has tons of data. And you, as a user, you access that data through their programming and through all of these systems that ought to magically make this stuff all work. And then another interesting piece of this is, so you have tons of devices all doing this. But data centers talk to data centers. So how many of you knew that Canvas stores a lot of its data using AWS? So Canvas has its own databases. They store some of their own data, and then they offload some of it to AWS. So if AWS is down, then Canvas is down. Or sometimes parts of Canvas will work, like you can see your classes, but you can't see your assignments or something like that. Depends on like which parts of the data are stored in Canvas and which of it are stored in AWS. So now, in the modern era, all of this is also the realm of the programmer, right? If you're writing Facebook or if you're writing Canvas or something like that, you have to know how an individual machine works and how data moves back and forth from registers to RAM to disk and so on. And you have to keep all of this in mind as well. Data is going across a network. There are vast quantities of data. And that is essentially the new challenge. So here's the internet, and that's what's making this interesting, and that's what's, we're going one step further in the data challenge and expanding it out from, few gigabytes or hundreds of gigabytes out to terabytes. And I always like to show this when talking about the internet. This is the internet as of 1969, and there's Utah there, one of them. So Utah was 1/4 of the very first original internet. And here we are studying big data now, which is only made possible by the internet. Anyway, interesting sidetrack. So the challenge here, and you've probably heard this term big data, which is a buzzword, so be aware of that, but basically it means lots of data. And it produces its own different challenges. So vast amounts of data. Does that really matter? Like, we know good data structures for storing data, and they have logarithmic growth properties. So even if the data gets massive, logarithmic growth means it's not a big deal. But we're not just talking about the algorithmic performance. We're talking, once you have vast amounts of data that don't even fit on one disk, you have different challenges. And then fast access or combination or filtering of data. So, say you're Facebook and you want to find the information for one user when they log in. And then you want to find all of their friends. And then you want to find all of their friends' friends. Facebook has algorithms that do all this kind of weird stuff. So they have to be able to take all these levels of indirection, combine your data with some other data based on some criteria, filter on some criteria. There are like terabytes upon terabytes of all of this data. Very different challenges than storing like, 1 million integers in a tree or something like that. And then it has to be always available, always securely accessed. It has to be available for simultaneous multiple users. So just whole new levels of challenges here. Stop me with questions, by the way, if you have them. I know this is just kind of basic intro stuff so far. Okay, so let's think about this. Let's say you're making something like Canvas. So you need to store a bunch of students. So a student is like a name, a major, a GPA, and you need to store them on disk somewhere, because if the server, you need to shut it down sometimes. You can't just store it in memory. And there's not only is there not enough memory capacity, but if the machine shuts down, you want the data to persist. So option one, let's say we just write some silly like English description of a student, like Jane Doe is a film major with a, so there are all these like useless English words in here, is a, with a, and is, things like that. This is how we as humans would record information on paper. So, ignoring the fact that we can get rid of all of those words that a computer doesn't care about, maybe, fine, let's do that. But then there's this question, how do we search for a particular student? Say I know the student's name, I want to know their GPA. How would I do that? Yeah?
Presumably by creating a data type with a number of variables.
Okay, so if you change the data structure, maybe yes. How would we do it with this data format? If I just had a big text file with a bunch of sentences like this, how would I find a certain student?
You have parsing characters to separate the information.
Okay, so you look at characters, right? So how many characters do I have to look at to find the student I'm looking for? Like, what is the algorithm here? Yeah. Right, so we try to match the name that's given with the, say like the name, we always know that the name is the first two words in the sentence. And then we would have to just scan through the entire file on average before finding the student we're looking for. So first of all, we have to know the data's format. This is assuming that the name is like the first two words. Second of all, it's extremely slow if I have like 1 million students. Okay, so here's maybe option two. Something like JSON. This is not JSON syntax. I've taken out tons of curly braces here, but this is basically JSON minus the curly braces. The point is that it's self-described data or self-tagged data. So I have major : film now. Now I'm saying the thing after this colon is something called major. So I now have some kind of like better information about the data itself. So how do we find all students enrolled in 2420? Still the same algorithm basically. Linearly scan through this giant file containing a bunch of text. We at least know where to look now in each block of text, but it's still going to be way too slow if I have 1 million students. Okay, XML, basically just kind of an alternative to JSON. So it's good in that the data is self-tagged, but still has the scalability problem. Okay, so let's think about this. We've sort of solved one of the problems. We have computer-friendly data in that it's tagged, but we need it to be fast. We want to be able to take 1 million or 1 billion students, and we want to quickly find one of them based on some criteria. So we want to store a bunch of student records. We want to be able to quickly add, remove, search, and enumerate them. You've all taken some kind of data structures class. What data structure should we use here?
Maybe a dictionary.
Maybe a dictionary, a hash set or something. So hash set solves the first three problems here, but it doesn't quite handle the enumerate operation. So is there an alternative data structure to a hash table?
Binary search tree.
Maybe binary search tree. Perfect. It does compromise a little on add, remove, search. It's a little slower than a hash table, but it supports enumeration. Okay, so yeah, maybe we make a binary search tree to store this data. Now, let's say not just students, I'm saving students and courses and professors. So that kind of looks like this. Okay, so I have some file somewhere that has all of the student records, some other file that has all the course records and professor's records. So each one of these is structured. So a student has a list of classes, a name, an ID. A professor has a list of classes that they're teaching and a name and ID. So each one of these files contains the same types of records, and they are all structured amongst themselves. Now let's say I want to ask some questions about this. Questions that you might very well ask of a Canvas-like system. So find all courses that a particular student is enrolled in. Okay, that's easy. I just go find the student, and it has a list of those courses, because that's already included in the student record. But then it gets a little more interesting when I have to kind of cross-reference between pieces of data. So find all teachers of student Z. So find some student by name, and then find all of their teachers. So I have to, that's not included in the student record, but it's kind of indirectly there. I can find their classes, and then maybe go use that info to find their teachers. Or even more challenging, order courses by how many students are enrolled. Courses do not have an enrollment saved directly, but I can indirectly get that information. So if I take one of these pieces of data, I can go find another piece of related data in this other table or other record of file of records. Similarly, going like two or three steps of indirection, I can find teachers of a particular student. Okay? Now, so we want to do these interesting queries that involve like filtering or combining different types of information. And now imagine there are millions of records in each of these boxes. So millions of students, millions of courses. It's not true for one university, but it would be true like worldwide. And these queries happen very frequently. Millions of users logging in, clicking on buttons on web pages that generate these queries. Okay, so the first part of the solution we saw to this problem was the data has to have some kind of structure. We can't use like natural language processing to try to like figure out what the English sentence means and extract out certain pieces of information. So we have structured data, meaning a student has exactly known pieces of information associated with it. A department, a number, or sorry, this is a course, not a student. A department, a number, and a name. So it has known fields, and the types of those fields are known. String, int, string, and so on. So unstructured versus structured data. Obviously, structured is much more amenable to computers because we can programmatically look for certain tags. Okay, so that's the first part of the solution. Then storing the data itself. We can't just have a big text file of students or courses or whatever in arbitrary order. So we save not just the raw data, but alongside it, we save a data structure, like a binary search tree or a hash table, depending on what we need to do. So that solves the quickly finding, searching, inserting, deleting problem. And the structured data solves the how do I know what this information means problem. So, an example. Here are 4 student records. They are structured. Each one of them has exactly 4 fields. All of their fields have a known type. Now, let's say I might want to ask, find a student by name. Okay, we can make a binary search tree that is built on their name, and I can quickly find a student. What if I also want to find all students with a GPA greater than 3.5? So can I use the same binary search tree, my name binary search tree? No. But we can do this. Here's one BST that orders the students by name. So the tree itself does not contain the information. It just contains one key. So this tree is built on names, and I can use this tree to quickly search by name. Here's another BST that's built on GPAs. And again, the nodes themselves just contain a key plus a reference to the actual data record. So there's one copy of the raw data somewhere, all of the records. And then in this particular case, I also have additionally 2 structures that allow me to search for that data based on different criteria. Meta information. So these trees are information about the information. You could imagine maybe a third tree that orders them by major or something like that. Okay. Now we need a language. So I can't really necessarily predict what kind of questions I might want to ask about this data. So find all students in a certain course, order students by GPA, whatever. If I wanted to, ask arbitrary questions about this information, and say we just have a BST, a binary search tree implemented in Java or C or something, then I might need to do something like this. So let me just draw. I might write a function, something like get students by GPA. And maybe I can pass in like 3.5, and the meaning of this is find all students with GPA equal to 3.5 or greater than, or whatever. It depends on how I write this function. And then somewhere in that method I would have a binary search tree traversal, and if I wanted to do a different query, I would have to write a new function, and I can't predict all the stuff that would happen. We could do it though, it would work. But better is define a language that is specifically designed for querying data. And so select name. Name is one of those fields of a student record. From students, that is the list of students, where GPA greater than 5. And then I could change this. There are certain keywords in here, there are operators. It's a language that I can express any query I want without predefining in the program or in the data how I need it to work, and problem solved. So this, though, is exactly what a database is. It defines a language, plus it has the mechanisms for efficiently storing structured data. So a database gives you these data structures, binary search trees, or hash tables, or whatever they may be, plus it gives you a language for querying that data. So this is why we study databases instead of rolling our own solution, which you certainly could. You're all good enough computer scientists by now that you could, given enough time, implement your own solution to this problem from scratch. It might be super slow or crappy, but you could do it. But the amount of time you had spent would be 100% wasted because lots of smart people have already figured this out. So tons and tons of research has gone into how to do this. How to make the data consistently available, and concurrency. So lots and lots of users asking questions about the data at the same time. It's all been figured out and implemented already for you. An interface for doing this. Languages have been developed for querying data. So don't reinvent the wheel. One of the most commonly abused anti-patterns is reinventing the wheel. So we obviously won't do that. We will learn how to use existing database systems. Questions? All right. So a database system has 2 major components. The DBMS, Database Management System, that's basically the engine or the underlying core machinery that makes all this stuff happen. So it has those data structures. It has trees or hash tables or whatever. It also interprets the query and figures out how to go look through those trees or hash tables to find the information. And then it has a language, so a way of expressing how do I search for data, what data am I looking for. So here's the roll your own solution. You as a programmer, you write some C or C# or Java or whatever program. All of those languages are going to give you access to some I/O library, right? Open a file, read a file, write a file. And then the OS will handle all of that. The OS is responsible for files. And then it'll figure out how to write it to disk. Or you as a programmer, so you're still writing C or Java or whatever, you use an SQL library or some kind of query language library. That's what the QL stands for. Your program interfaces with another language, a query language, which then interfaces with a DBMS, and it's doing all kinds of smarts and has this translation layer, and eventually the OS and the disk still have to get involved, right? You have to save the bits somewhere, but these two pieces inserted here make it much, much smarter and more powerful. So option 2, you as a programmer, interfacing with SQL. So SQL is not just you open a command line and you type select name from whatever, you type some SQL command. You can obviously write programs that generate SQL commands. So you could do it through a command line. Or maybe Facebook does something like this. Facebook is a program that interfaces with a database. It programmatically generates some kind of query. Maybe it doesn't use SQL, but suppose it did. It uses some kind of database. SQL Workbench is the thing over on the left. So the command line and the SQL Workbench are both like direct interfaces to the database where you can just say, select certain information out of certain records or whatever. And then you can write any number of programs that automatically and dynamically interface with the database, but still via the query language. Okay. So, this class. We kind of start with the basic principles of structured data. So structured meaning I know what the fields are, I know what the types are, I have some well-defined record for an individual object or piece of data. And that may sound simple and arbitrary, like I just showed. Well, you just put like a name, a colon, and then a value. Like that's basic structured information. But there are principles behind how do you structure the information. It's not just go off and do anything you want, or the DBMS will not really work. So there are like forms of mathematics that were invented to efficiently express structured and related data. And we'll kind of go over the principles of how we design structured data. And then application of databases. So write a program that uses some database to represent a Canvas-like system or something like that. And then we will get to how does this all work under the hood. So how does it build these data structures or trees or hash tables or whatever? How does it execute the queries and find the information? So you have to understand enough about that to know what you're doing to avoid falling into performance holes or security holes and stuff like that. Okay, so the assignments. This is not really a programming class, but it will involve programming. I will teach you basically nothing about programming or any particular language other than SQL. But it's just kind of expected and assumed that you can program. I think that is true of everyone here. So some of the assignments will involve a little bit of programming. It'll be pretty easy. The challenge there is the SQL part, not the programming part. And then there will be written assignments. Just produce a PDF and hand it in. Like answer some logical questions about sets or as I mentioned, there's a form of mathematics. Don't let that scare you. I know that sounds like, oh, there's math. It's really not that bad. And then some of the assignments will just be take your database and put some stuff into it, or generate some queries that do a certain thing. So speaking of which, you all will have your own database on our server. So the way this works, there's one server. It's the one machine. That doesn't mean there's one database. This one machine can have many, many databases on it, and each of you will have your own. Completely isolated. You won't be able to see other people's databases. It'll be as though this is your own server. But really, other people might be doing things that will cause it to slow down, and we'll try to keep an eye on that and kill any commands that are misbehaving. But this is, you'll have your own server, your own database here for doing assignments, doing the project, doing all kinds of things, and you'll be using it throughout the semester. And me and the TAs have access to all of them. So that's basically how we'll know, well, did you generate the right data and update your database correctly? Okay, so there are the assignments I mentioned. Those are smaller, usually like weekly, maybe 2 weeks at the most. And then there's a project which will be going on throughout the semester in multiple phases. The project is basically implement a Canvas-like systems. It's called a learning management system. It tracks students, courses, professors, grades, things like that. So it'll be a web server, just like Canvas is, but I don't care about like the interface part. That's not what this class is about. So the interface is given to you. All of the JavaScript and CSS and HTML is done for you. You're implementing the backend, which is, so somebody clicks on a button, it'll invoke some function. Your function has to decide, all right, this student's trying to enroll in a class. Query the database to figure out if they're eligible. If they are, update the database appropriately. So you'll just be programmatically generating database updates and queries, basically. Okay, 2 exams, 1 midterm, 1 final. 5 pages of notes front and back, so I'm not big on memorization. Try to use the opportunity to write these notes as you're studying. That's why I do this. Writing down notes and trying to figure out what it is you don't know is, then you don't even need the notes. But so it's kind of this weird, you have to make them in order to study, but then they end up being useless in the end. Like you could make them and then just throw them away. Grading breakdown, midterm and final are worth the same amount. That's kind of the only interesting thing here, really. Okay, so I'll go through kind of the major phases of different contents. So the first part of the class will be more like fundamental principles behind how to design a database. How do you design the representation of data in a good and clean way? Relational algebra is that math I was talking about. We talk about just principles without even getting into SQL or any specifics of any database. We talk about just how do you structure information. And then we'll get into specifically SQL, using SQL inside of C#. C# has this excellent thing called LINQ, Language Integrated Query, which basically means you can write SQL queries directly inside of C# and they result in C# objects. There's this translation layer going on under the hood, which queries the database using real SQL, gets some information back, converts it into an object. Really cool. Talk a little bit about just the basics of web servers and where database manipulation fits in there. And then we will get into under the hood, or how does the engine work. So turns out it's not actually binary search trees. It uses something called a B+ tree, which is a search tree, a form of search tree, but specifically designed to handle the challenges of vast quantities of data. and R trees. Depending on what kind of data you're storing, you might use a different kind of tree. Turns out trees are everywhere. So, they really are used just everywhere in computer science. We use Visual Studio for the programming for the IDE. So C# is the programming language. SQL is the query language. So like I said, I'm not going to really teach you C#, maybe just a couple of the specific things related to SQL that you need to know, and then it's up to you to, I assume you know how to program. MySQL is the database engine we will be using, and we will actually use Linux as well. So in addition to that database server, you also have your own Linux VM, which is where you will deploy your web server. So there are a few little hacky Linux commands you'll need to know, but don't let that scare you too much. Okay, any questions while I'm just cruising through this boring stuff? Yes? So entity relationship model here is a way of formally defining what is the data in your system and how does it relate to each other. So as an example, students and professors. Students and professors are both entities. What are their relationships? And it's just it's like a way of formalizing those definitions and relationships. And we do that before even thinking about queries and SQL and databases in order to get the right design before going and implementing stuff. Just like you design a program before you even touch the keyboard. Okay, so Visual Studio means Windows. And it does actually have to be Windows because the Mac version of Visual Studio does not support the things that we'll be using. I recommend Boot Camp if you're on a Mac. Some VMs work. Parallels has been known to work well. Other VMs are just kind of slow and you'll have a really bad Visual Studio experience. But yes, you do need Windows. You need Visual Studio Enterprise 2017. It's free. You all have access to this. Most of you even already have it installed if you've taken 3500 from us. There are instructions on Canvas already how to do this, how to install Visual Studio, how to install Windows on a Mac. We're not your system administrators. This is all up to you. We assume you can figure out how to do this by now. Canvas, as I've already mentioned, you will use it extensively. Assignments, handout, grades, everything like that, all on Canvas. So we will post help hours and office hours soon once I've kind of figured out when the TAs are available, when I'm available. You won't really need help until the homework goes out, but I'll let you know as soon as I can. And then we're using Piazza forums. How many of you have used those? Okay, good. Pretty much everyone. Way better than Canvas forums. So just, they won't even be there. I won't even create any. Sign up for Piazza. The link is right there on Canvas. You just click it and you're in. It's, basically you ask and answer questions of other students. We will also answer questions if no satisfactory student question has been answered yet. Pretty straightforward. One more thing about Piazza. Use that for contacting us, the course staff, me and the TAs. Don't use Canvas. Email is okay, or Piazza. You can post a private message which goes only to the staff. That's as good as sending email to all of us. Okay, we have 5 great TAs. Those of you who are here, please stand up. Atul, you're not paying attention. Atul, Seth, Jake, Josh. Am I not seeing? Okay. So Prasid is missing, but anyway. Hello, everyone. Hello, TAs. Get to know them. I have to talk about cheating. Cheating's dumb. Don't do it. We catch cheaters every semester. There were 31 cheaters caught in one class last semester. It was a big class, but like people think it doesn't happen. Like, yes, we catch cheaters and they fail the class. It sucks. Point is, why would you cheat if, why are you here? Cheating completely nullifies any reason why you think you're here. You're here to learn. You're not just here to get a degree. If you cheat, you're like, well, I can get a degree by this cheating. Then what good is the degree? What is it going to accomplish by having a meaningless degree? So, okay, don't cheat. Let's take, before we actually start getting into, real material, in these 80-minute classes, I like to take a break in the middle. So let's take a 4 or 5 minutes. So, SQL is what's called a relational database, and we will be studying pretty much entirely relational databases. We'll talk about non-relational databases a little bit at the end, but relational databases are the ones that have been thoroughly studied and developed. And basically what this means is it's a form of structured information storage where we define one or more relations. So a relation is a set of directly related values. So here is one relation. ID, name, date of birth. So these things represent just a person of some sort. They are directly related because the date of birth is just that person's date of birth. The ID is just that person's ID. So they're stored basically next to each other, at least when we think of it visually or draw it anytime. As to where it actually gets stored on the disk is a whole other matter that we'll talk about. But conceptually, in the design, we think of them as next to each other and directly related. And so we often think of it as a table. A relation is a table, can be viewed as a table. Basically, you have column headers at the top, ID, name, date of birth, and then you have values. So 1, 2, 3, and 4 are the IDs. Harry, Ron, so forth are the names, and then just dates. So here's a table representing one relation. And then unrelated data is put into another relation. So I have here maybe another relation called courses that has these two things are directly related, the course number and name. So CS 5530 is directly related to the name database systems. They are not directly related to any of these people, but they could make sense to be indirectly related or to be in the same database because one of these persons might be able to enroll in one of these classes or teach one of these classes. So the name Harry and his date of birth has nothing directly to do with like CS 2420, but he might be a student in that class. So they're in the same database, separated into different relations. A relation holds only directly related pieces of data. So each table or relation has the header at the top, which is the information about the information, and then it has a set of tuples. A tuple is just one value for each column. So 1, Harry, July 31st, 3.5 is a tuple. So, yes, question back there?
Just wanted to point out there's something wrong with the database.
Oh, yeah?
There's no way for my NEC
So here's the thing. I've actually never read these books. This is funny actually because I kind of figured, for some reason, I figured Hermione would be like a good student, and And oh, it would be higher, you're saying?
Yeah.
Oh, okay. Oh, I see. Got it. Okay. I'll fix it next time. So question, does every self in this table need to be unique? The answer is actually implicitly here. No. Two people could have the same GPA, two people could have the same birth date. Obviously not. Don't need to be unique. Does every tuple need to be unique, or every row? Well, I don't know. Maybe not enough information here to answer this, but let's just think about it. What would it mean to have duplicate rows?
Oh, they have the same ID, which is a problem.
They would have the same ID, same everything. So how could there be two people with the same ID? And if there were, like, what would that even indicate? There's no meaning behind that. If it's exactly the same thing, why have two of them? Maybe you could say, well, we're trying to count them. Like, you can maybe have two Hermiones, but in this case, ID means identifier, so it would be unique. So by definition, actually, a relational database does not contain duplicate tuples. It's a set. Every row in a relation will be unique. Okay, so switching away from classes and school and stuff, let's do like a library example. So you have patrons with phone numbers, card numbers, you have books. So let's look at this. This is like a first attempt. This is saying Harry has checked out his own book, so Malfoy has checked out Dune or whatever. They have a phone number, they have a card number. So I said a relational database separates related data into different tables. Is Malfoy directly related to Dune? No. So Dune is a book, Malfoy is a person. Yes, in this table they are related in some way. Malfoy has checked the book out, but not directly. The book is a separate entity that can exist without any person. So no, they are not directly related, only indirectly. This means this is not a good relational database. This is not a proper relation. Here's one of the, like, who cares? Why can't we just, why do we need relations to only have related data? What if one person checks out multiple books? So, now I know those of you who took CS 3500 from me have seen this. It's only today. All right, we will quickly move beyond that. Here's maybe one option. He's checked out Dune, Hyperion, and Bonnie Meadows. That's a book I just made up. Okay, it works. Like this has the information. There are no duplicates in these tuples. But there is a lot of duplicate information. So, listing the name, the phone number, the card number multiple times is all just useless and wasted. So if we had like somebody who's checked out 20 books, we'd have their phone number in there 20 times for no reason. So, okay, maybe we make a list. So we just have their name once, and then we have a list of ISBNs and a list of titles. Now, problem with that is, remember, the database system, the underlying engine, is going to build data structures on some or all of these fields. So let's say it builds a data structure on the book title, a binary search tree of all of the book titles in this table. How do you build a binary search tree where some of the items are single books, like Harry Potter, and some of the items are a list? Like, how do you compare a list to a single item, and where do you put that list in the binary search tree?
Make a list of length 1.
Make a list of length 1, and then still, how do you compare a list to a list? Where does a list go in relation to another list in a binary search tree? it's a problem. And the solution to the problem is don't make a list. So, like for example, how would we find all books that start with H? Maybe make like another data structure inside of the data structure. So you have a tree, and then for anyone who's checked out multiple books, make another tree inside of there. It just gets very messy. And the question of like the general kind of queries we want to do, like find certain books or certain people who've checked out books, starts to get very hard to reason about if we have these weird mutable types. So, this for this reason, for the reason that the database system is building structures around these, and we want to be able to carefully and logically reason about relationships between data, we avoid lists. Okay, so we still haven't answered, well, what do we do then? Like, how do we check out multiple books? We'll get to that, but here's another problem. What if somebody has checked out no books? We could put null in there or something, but that still just kind of muddies the meaning of the data. What if somebody has two phone numbers, home number and a cell number? So maybe we do this. We say Dan with this phone number, Dan with the other phone number, and then if they've checked out multiple books, then you have two phone numbers times 2 books, and we start to get this like multiplication of duplicated data. Like, why is the name Dan in there 4 times with the same card number? It's the same person, and we just have all these wasted rows. So the first solution is let's take advantage of all of the theory and research that's gone into this, and let's make it a relational database. If 2 things are not related, don't put them in the same table. So patrons, only related information, name, phone, card number. And then inventory or books. ISBN is directly related to book title. Okay, so we've solved that problem. Now, why does this help? Or how now do we actually, so here's another question. Now, how do we say Malfoy is checked out Dune? Yeah.
Could you make like another table that points like patrons to inventory?
Right, so make another table. This other table is essentially like a hopping point, or it's just adding a level of indirection. So now I say, here are the patrons, here are the books, here are the books that are checked out and by whom. So this third table here has taken one critical piece of information from the patrons table and one critical piece from the books table, and that is what links them together. So these 2 pieces of information have to be carefully picked. There's one identifier for each. And now I essentially have a way of indirectly saying, all right, here's a person. I can take their card number, go over here, which gives me an ISBN, which says this person has checked out that book. So now if somebody checks out 2 books, yes, I do have to say, in some way, I do have to say this person shows up in the checked out table twice. But instead of being their name or all of their information, like name plus phone number, it's just one small identifier, card number.
Then aren't you also going to have to, like if you wanted to say, like I don't know, assuming that there's going to be a lot of checked out requests, like that table's going to fill up a lot. Like if you were like, I want to find out all books that Harry has checked out, you have to linearly search.
So, good question. So let's say this table gets big. Lots of books checked out, lots of patrons. And I want to find all of the books that Harry has checked out. So this gets back to the question of how do I quickly find something out of a big blob of data? And the answer is probably every single one of these columns in every single one of these tables will have a tree built around it. So I will have a tree built around cardnum here, and I can say, all right, I'm looking for books checked out by Harry. Use the name tree to quickly find Harry, which points me to the cardnum 1, 2, 3. Then take the cardnum, go over to the checked out cardnum tree, quickly find 1, 2, 3, which would then, they would all be next to each other in order. So I go quickly find the first one and then just step through. It gives me all of the books that Harry has checked out. So building data structures around each one of these or most of these columns is what allows us to quickly get from here to there and answer questions based on whatever criteria. Okay, any other? All right, does that answer your question? So here's how we represent somebody having no books checked out. Now that we have separated data into relations, we just say there is no tuple in the checked out table for Harry. This means Harry has no books checked out. Harry still exists. He's still a patron of the library. And some of these books are not checked out, but they still exist. Okay, now what about the multiple phone numbers problem? Yep.
Make another table that stores phone numbers.
Make another table. So now just by definition of the problem, we have to think about what are the relations. So phone number is now no longer directly associated with a person. It's now in its own table that is indirectly, we can get there by cardinal, we can get back to the person that belongs to that phone number. And now we can have multiple phone numbers. The only duplicate thing in there is this little key, the cardinal. Okay, so the way this is all, yeah, question first. So yeah, there's kind of a conflict between the strict definition, like what is directly related. A phone number does belong to a person, but the way that we have defined the full problem now is we have said a person can have two phone numbers. So that kind of breaks the English meaning of directly related, and then we now say a card number plus phone number is a relation by itself, and a person does not directly have a phone number. And so that is kind of where the difference between like intuitive English meaning and relational database meaning starts to separate.
So is the card number sort of the key that's going to be used to sort all the data structures?
So is the card num the key that will be used to sort all the data structures? There will be a data structure built on card num and a data structure built on ISBN and book title and person's name. So let me just cruise way back quickly. We can have the raw data somewhere. The orange boxes here are people. That's the raw data. There's only one copy of the raw data, but we can build multiple data structures that reference that data. So I have two binary search trees here, one of them built on name, one of them built on GPA. This allows me to quickly find, in this completely arbitrarily ordered blob of data, this allows me to quickly find one of them based on name or based on GPA. So I could build another data structure on ID or another data structure on major. And even though the data only exists in one place and in some arbitrary order, multiple data structures that indirectly reference the data is what allows me to find data quickly. Does that answer the question?
Yeah.
Okay. So kind of actually this same topic here. So the way that we are indirectly relating data is by some critical piece of each one of these tuples. So card num and ISBN are unique identifiers. Card num is a unique identifier for a person. ISBN uniquely identifies a book. Those are critical fields, and those are what I use to get to, like, hop to other tables and indirectly reference and link pieces of data together. So the checked out table, for example, has just card num and ISBN. The reason it has those is because card num is the key for a person, ISBN is the key for a book. So having these like same type, same name columns in different relations is what kind of gives me the links or paths to get from some data to some other indirectly related data. Okay, what if we have multiple copies of the same book? A real library obviously has this. And, yep, like another table. So here's the full library. Question first, back there.
Alternatively, could you not just add a quantity field to the book table, to the inventory table?
So could you add a quantity field to the inventory table? That would be one perhaps solution, but then that doesn't really give me multiple books. Like, so how does that differentiate the copy of Dune that has a copy stain on page 7 versus the copy of Dune that doesn't? So there are actually two entities here. We don't always just want to count like how many of them. We want like this book versus this book. They have the same title and ISBN, but they are separate actual entities. So here's our full library. We've got patrons checked out and phones, kind of like what we've seen before, but now I've changed the way that books are represented. So I have titles and I have inventory. Titles is just a list of all books that have ever been published. This is not my library's books or any library's books. This is like the global list of publications. This is the Library of Congress or something. And then inventory is my copies of certain books. So I use ISBN to identify the title and author to go into the titles book table. And then I add an additional piece of information, my own library's serial number, to uniquely identify my copies of that book. This allows us to easily represent, my library has multiple copies of some books. So that first one there, ISBN ending in like 5427, I have 2 copies of that. I have no copies of Dune in my library, and even though Dune is a book that exists. So this easily and naturally just represents the information that a library might want to store. Okay, so how do we, we've got all the information. How do we find all books checked out by Joe? This is like a straightforward query that we might want to do in a library. Yeah.
Step 1, find the card number associated with 2. Step 2, find all the entries in the back card number in the checked out table. Step 3, check.
Yep, okay, so let me just stop you there. It sounds like there are multiple steps. Yes, that's exactly kind of the point. The only information we have is Joe. So we have to go there first. We go to Joe. We know that Joe is a name, so we go to the patrons table, we find Joe. Because there is a tree built around the name column, we can quickly find Joe. That gets us to his card number. That lets us search in the checked out table, which gets us to some serial numbers. That lets us search in the inventory, which gets us to some ISBNs and so on. Now, you know, we've dereferenced, we've gone through like several levels of indirection, but we have found all of the books checked out by Joe. We can get their title or author or whatever we need. Okay? So, the basic goal here is we store an individual piece of data is an atom. Atom just meaning indivisible. So it's one piece of information. Basically, this means don't store lists or arrays. The way that we did this is we separated data into different relations so that Joe has 2 books checked out. How do I represent multiple things without a list? By doing this. So there are only atoms here. Joe has a single atom name, a single atom card number, which gets us over to some other table, and so on. Yeah?
Suppose for the sake of argument that Joe has hundreds of thousands of books checked out. Will this not take a very long time?
If Joe has hundreds of thousands of books checked out, it will be at least a linear time operation on the number of books checked out. But there's no getting around that. How else would you get around that? If Joe has hundreds of thousands of books checked out, yes, it will take a long time. Yep.
When you're designing a database, is the answer always to choose when you have a one or more kind of entity, always to make a separate table if you're not serious in the beginning?
Right, so if you have, when you're designing this thing, if you have a possibility for greater than one of something, if you know the exact number, like if it's 2, then you could maybe just make another column, like card num 1 and card num 2. If it's unknown and greater than 1, then you split it into a separate table. Generally, yes. So don't store lists and arrays. Instead, build compound information by referencing other tables, exactly like we did for our library. What this does is, so this still might seem kind of weird, what this does is enables the database engine to do its own optimizations because it's simpler to reason about the information and how the information is related. Lists and arrays just complicate things, like how does it relate a list to a single item or something like that. It basically, it lets us and the database system more powerfully reason about the data. It's a design principle. And it enables the database management system to optimize. So the purpose here, the end goal is we want a general purpose, queryable, huge chunk of data, and we want it to be fast. So if we knew we were only exactly ever going to be doing one certain query, then yes, we might be able to optimize better than a MySQL server. But if we don't know really what we're doing, then MySQL and designing relational databases just gives us this powerful tool and framework for defining arbitrary databases and quickly using them, accessing them, manipulating them. Bad news is SQL will let you violate the good design rules, just like any programming language will let you violate good style. So because of this, we design databases without even thinking about SQL first, using a more abstract and formal way of reasoning and describing data. So jumping right into that, what are these formal definitions and languages for describing related data, relational data? So here's a table or a relation. A relation is comprised of a schema. The schema is like the information about the information. It defines the structure. So name and type of every column in the table. An attribute is a single column header. So UID is a uint, or sorry, SID is a uint. That is one attribute. And then this is the schema. You know, right here I'm showing a full relation. The schema is just this information, just the set of attributes. So the schema, we can reason about data and information without even seeing any actual data, but we can just use the schema to reason about, like, well, how costly will it be to, like, combine these two tables or relate them in a certain way. And then the data itself is called an instance. So you have the schema at the top. All of the tuples contained within are the actual data. This is the instance. And then each one of these things in the instance is a tuple. Just one row. We've already kind of talked about that. So here is a relation. All that stuff put together. Here are two relations. So don't think of this as like there's one relation that defines the students. We can reason about relations, multiple relations at a time. So relation 1 here, maybe relation 1 is every student. And maybe relation 2 is a subset of relation 1 after asking for students with a GPA of 3.5. It's a compatible relation because it has the same schema. The key here is that we can deal with multiple relations. Yeah. So the attribute is an identifier plus a type, plus additional restrictions that we'll talk about soon. For now, think of it as basically just the name and the type for structuring the data. Okay, so it's important to note that the instance is a set of tuples. Set means, what does set mean? No duplicates. Somebody said it. Yes. That means there can be no two rows that have the same pieces of information in every field. Now, there can be two rows that have the same pieces of information in some fields, like GPA here. Harry and Hermione have the same GPA. But the combination of all fields makes unique tuples for every row here. Yes, obviously we can have duplicate data somewhere. It's possible for two people to have the same name, for example. So, question though, if it's possible to have duplicate data somewhere, then how do we guarantee that each tuple is unique?
You have an ID like that.
That is exactly why the ID column here exists. Like, ID here is kind of useless. It doesn't tell me anything about these people. Like, I don't care what any of your UIDs are, but I need them because I need to uniquely identify you. That's the only reason it exists, is to uniquify every tuple. And this is called a key. When defining a relation, we have to specify a key on the table. So the key, I'm saying in this case, the key is the SID, and I'm therefore asserting that every SID is unique. Yeah. At what point is this enforced? This is enforced when we create the table in SQL. Or, let's not even think about SQL yet. I am enforcing it right now by saying that this attribute is a key. Now, in an abstract sense, this now says that this relation has a key on this column. And without even knowing how to do that in SQL, I know something about this relation now. So here's a table with a single column key, but keys can be multiple columns. So here's like another example, cars. Maybe car plus model, the two combined makes up a key. Because I can obviously have multiple copies of Toyota in here. If this is just a list of all types of cars, so not any specific car, not any like VIN or anything, but just like a list of car models. Toyota can obviously show up multiple times, so it can't be a key. Any particular manufacturer could show up any number of times. Any model probably won't show up multiple times, but it is possible for two companies to make a car with the same name, like F1. Lots of companies make an F1 car. So neither of them by themselves are unique. F1 could show up multiple times, Toyota shows up multiple times, but the combination of them both makes the key. So there cannot be two Toyota F1s or Toyota Camrys. what would that mean? I'm just listing all of the types of car models. Listing Camry twice is meaningless. Okay, so as a database designer, it's your job to define what the keys are. So you would say, all right, I'm making a students table. And since this is a relational database, I need a key. So if there is no combination of the existing fields that is unique, then you have to add an identifier, and that's why SID was added here. The cars example, you can just say make plus model is the key, because I know those will always be unique. But before doing that in SQL, we need to formally think about what does uniqueness mean in a relation. Why is it important? How does it like help us reason about the data? So I'll leave you with a definition for today that we will explore further next time. So a superkey is any set of fields such that no two tuples have duplicate values in those fields. Now, that is different from a key. So this is a super key. There's also something called a key, which is more restrictive than this. But basically, this is the basic formal definition that we will need to reason about what the data means and how we restrict the data's structure. And we're out of